Here we introduce the individual computing unit that makes up neural networks. Neural networks are called neural because their origins lie in the McCulloch-Pitts neuron, which was a 1943 simplified model of the human neuron, modeled as a kind of computing element described in propositional logic. But the modern use of neural networks in language processing no longer draws on these early biological inspirations. So the name neural is really just kind of a historical remnant. Instead, a modern neural network is a network of small computing units, each of which takes a vector of input values and produces a single output values. Over the next few lectures, we'll introduce these units, see how they connect together into feed-forward networks, so-called because the computation proceeds iteratively from one layer of units to the next. The use of modern neural networks is often called deep learning because modern networks are often deep, meaning they have many layers. But the building block of a neural network is a single computational unit. A unit takes a set of real valued numbers as input, performs some computation on them, combining with weights and biases and a nonlinear transform, and produces an output. Let's see this in more detail. At its heart, a neural unit is taking a weighted sum of its input plus one additional term in the sum called a bias term. So given a set of inputs, x1 through xn, a unit has a set of corresponding weights, w1 through wn, and a bias b. And so we can represent the weighted sum z as the bias plus the sum. Often it's more convenient to express this weighted sum using vector notation. So a scalar z is computed from the dot product of the weight vector and an input vector plus a scalar bias b. Finally, instead of just using z, a linear function of x, as the output, neural networks apply a nonlinear function f to z. We'll refer to the output of this function as the activation value for the unit, a for activation. Since we're just modeling a single unit, the activation for the node is in fact the final output of the network, which we'll generally call y or y hat. We've already seen the sigmoid for logistic regression, 1 over 1 plus e to the minus z. And the sigmoid has a number of advantages. It maps the input into the range 0 or 1, which is useful in squashing outliers toward 1 or 0. And it's differentiable, which, as we saw, is handy for learning. So we'll use the sigmoid nonlinear activation function as our example in this lecture, although we'll soon see that there are other kinds of nonlinear functions. So here's the function that a simple unit with a sigmoid activation function is computing from an input x, a weight vector w, and a bias term b. So we're just taking the sigmoid of w dot x plus b. And here's our picture of the unit again, showing the pieces, the input, the weights, the weighted sum, the nonlinear activation, and the output value. Let's walk through an example just to get an intuition. Suppose we have a unit with a weight vector of 3 weights and a bias. And let's suppose we have the input vector x1 is 0.5, x2 is 0.6, x3 is 0.1. Let's compute the sigmoid. So we'll want to compute 1 over 1 plus x of minus w dot x plus b. And let's now write out w dot x plus b. We'll have 0.5 times 0.2 plus 0.6 times 0.3 plus 0.1 times 0.9 plus the bias. And here I've got that all printed neatly. And if we just run that computation, we get 1 over 1 plus x of negative 0.87, or so our sigmoid output for this particular input is going to be 0.7. We did that computation with the sigmoid, but in practice, the sigmoid is not commonly used as an activation function. A function that is very similar, but almost always better, is the tan-h function, a variant of the sigmoid that ranges from -1 to +1. So that's e to the z minus e to the minus z over e to the z plus e to the minus z. The tan-h function has the nice properties of being smoothly differentiable and mapping outlier values toward the mean. But the simplest activation function, and perhaps the most commonly used, is the rectified linear unit, also called the ReLU. It's just the same as z when z is positive and 0 otherwise. The ReLU function has nice properties that result from it being very close to linear. In the sigmoid or tanh functions, very high values of z result in values of y that are saturated, meaning extremely close to 1, with derivatives very close to 0. Zero derivatives cause problems for learning. Gradients that are almost 0 cause the error signal to get smaller and smaller until it's too small to be used for training, a problem called the vanishing gradient problem. ReLUs don't have this problem since the derivative for high values of z is just 1 rather than very close to 0. We've introduced the basic neural computing unit that underlies modern neural networks.